reason why this variable voltage source was here is to measure the maximum kinetic energy of the electrons. Okay, this is made stronger and stronger. So if this is a positive, this is the positive side, and this is the negative side. So let's say that the electrons were coming this way, yeah? This voltage source would be made stronger and stronger to repel the electrons and see at which voltage do we not get any electrons anymore. And that voltage will give us information on the maximum kinetic energy of the electrons. Mm-hmm. The reason being is because by the time we're at this stage, we should know that EV equals half mv squared. Okay. So you know that this is kinetic energy. This is voltage. And this is electronic charge. So this EV is basically a statement saying that the kinetic energy that an electron has is equal to the voltage it was accelerated through. It was accelerated by. It's also equal to the maximum voltage which stops it, right? So if I have an electron and I have the perfect voltage to completely stop it so that the current falls to zero, then that gives me an indication of the maximum kinetic energy that it has, right? It makes sense, doesn't it? Okay. So there's more to talk about this experiment. Okay. So here they are with this experiment, shining light on different pieces of metal and seeing how many electrons are coming off and how energetic those electrons are. Okay. These are the current observations. So observations of photoelectric effect. So the first and very important observation is that red light of any brightness, did not release electrons. Okay, so they were shining red light, normal red light. They didn't see anything. So they increased the amplitude of the red light. They still didn't see anything. So red light, so this could be radio waves, microwaves, infrared, or just literally red light, right? Did not do anything to make photoelectrons. The second observation was that shining red light for ages also did not release electrons. What do you think that means?
I think that means that maybe the speed of the wave isn't sufficient, or the energy, the energy of the wave is not big enough to charge the electron so much that or to charge the electron so that it moves fast enough.
That is true, but that's actually to do with the first point. The second point is more to do with the nature of how energy is transferred. The wave theory of light, so all that we've been doing previously, the wave theory of light suggests that energy transfer is continuous. So when waves are traveling through a medium, like all these lessons that we've done before, where they've just been going up and down, and it's continuous. It's yes, between if the amplitude was between there and there, let's say that that's the scale of the amplitude, yes?
Mhm.
The particles can take an infinite number of values in between the amplitude. Is that not true?
Yeah.
It doesn't have to be 1, 2, 3, and then 4, and 4 may be the amplitude. It could be 1.1, 2.5, 0.333 recurrent, 0.00014 times 10 to the minus 6. It could be any value in between 0 and 4 that these particles can take. That means the energy transferred to these particles in the medium can be any value. That's what we mean by continuous energy transfer. It also means that the longer, or it gives the impression that the longer you shine light on something, then the more energy it builds up, because it's absorbing energy continuously. Is that not? That's basically what it implies, right? So we're saying here that, okay, so red light didn't work. Okay, let's shine it for longer. Let's see if we can build up the energy inside the metal. And maybe after 3 million years, we might finally see some photoelectrons. It obviously didn't happen, okay? The next observation, so I'm gonna write observation, and then below them, I'm going to modify it and write the reasoning behind it. The third observation was that blue light, which happened to be dim, was able to photo emit electrons. Okay, blue light was able to photo emit electrons, yes? The fourth observation was that making blue light brighter photo emitted more electrons, but did not affect their kinetic energies. And then probably a fifth observation was what was the fifth observation? Oh, probably the fifth observation was that using different metals or different light. So by different light, I could mean green, blue, purple, you know, slowly going from the bottom end to the top end. Using different metals or different light affected the kinetic energy of the photoelectrons. Okay, so 5 observations. Now let's go through the reasoning of why these 5 observations exist, or let's explain why they exist. Okay.
Yeah.
Or what they mean, or rather what they mean. So let's talk about the first observation. Red light of any brightness did not release electrons. What does that suggest?
So that is what I said in the beginning.
Yep.
That the red light does not have enough energy for the electrons to speed up when they absorb it. And how exactly do the electrons absorb this light?
So what happens is that, so you haven't done energy levels yet, have you?
I don't think so, no.
Okay, so
We'll probably move on to it from next week if we do this topic, which probably we will.
So you asked me how do the red light, how do the electrons absorb this red light? Well,
Yeah.
photons can penetrate into the metal. And what happens is that if a photon goes directly to an atom, the electrons surrounding the atom may absorb the photon. Sorry, not even atom. I'm talking nonsense. It's nothing to do with the atoms. In a metal, and it's nothing to do with energy levels either. I made a mistake. Energy levels is something similar, but it's different from this situation. We'll talk about it. So in a metal, you know how a metal has delocalized electrons?
Yeah.
Okay, so it is those delocalized electrons that we are seeing being photo emitted. Now, the delocalized electrons are in a region of space or metallic space called the conduction band. Conduction meaning they are free to move, but they are still.
When the light hits the metal, it gives energy to the electron and they move to the valence band.
No, valence band is the lowest band. Valence band is the one that is locked around the metal ions. Okay, so if the step is to go from valence band to conduction band, then from conduction band to free space, exiting the metal. So what we're doing, or what these guys are doing, is that they are shining photons. These energetic photons will be absorbed by the electrons in the conduction band, and the electrons in the conduction band will be able to fly out, or they will have enough energy to escape the conduction band and fly out in real free space. Yeah.
Okay.
So red light simply didn't have enough energy to promote electrons from conduction band to free space. Okay, that's number one. Observation number two. Shining red light for ages also did not release electrons. Wave theory of continuous energy transfer. So meaning that you could build up the energy over time. So wave theory of continuous energy transfer, not valid. Energy is instead transferred instantaneously, like a particle. Okay, so when you hit a snooker ball onto the blackboard or whatever, the energy is, it's instantaneous. Yeah. It's a lot different from shining, from building up, from thinking that you're gonna build up energy continuously by shining light for a while. The third observation: blue dim light was able to photo emit electrons. The ability to promote electrons not based on amplitude, so do you remember that expression that I wrote a week ago, or maybe last week or something like this, where you have E being proportional to the amplitude squared? Do you remember that?
Yeah.
Yeah, that's not valid here anymore. The energy that the light is carrying is not due to how bright it is. So the ability to promote electrons not based on amplitude. Instead, based on frequency or wavelength. So even dim blue light was able to photoemit electrons. So we now have E equals HF or HC over lambda. That is the energy that this light is carrying, or light photons are carrying. They carry energy like particles. Sorry?
What is C in this case?
Light speed.
Oh, okay.
Because all electromagnetic radiation travels at light speed. Yep. The fourth observation, making blue light brighter, photo emitted more electrons, but did not affect their kinetic energies. So amplitude does not affect the energy of the photons, but instead controls how many photons. Yep. So when they made the blue light brighter and they saw many more electrons being emitted, but they all had the same energy, it simply meant that you just shone more photons at the metal. So you were promoting more electrons with the same energy.
Okay.
And the last and final observation, using different metals or different lights, green, blue, purple, affected the kinetic energy of the electrons. And to that I say, every metal had a work function, phi, and that is the minimum energy required to photo emit. Okay, so every metal had a work function, and this was the tax. This is basically the not passport. This is basically the price the light has to pay in order to get that electron out of the metal. And then the energy that's left over is given as kinetic energy. So this therefore gives us the photoelectric effect equation, where you got half mv squared max is equal to HF, so the energy of the photon, minus the work function, the energy that you have to give to the metal in order to get an electron out of it. So this is work function. That is the energy of the photon, and that is the maximum kinetic energy. Okay.